Okay, I think everything works fine. Sorry for a little delay due to technical issues, but we are now online, streamed. We're connected to Professor Murawski from Lublin, who's going to tell us about the realistic numerical simulations of the solar atmosphere. And I just wanted to remind people here in the audience to keep distance, wear masks, ask questions, and people on Zoom, you can just ask questions. You don't need to keep your masks on. Okay, Professor Murawski, please.
Okay, good afternoon. It's a pleasure for me to give a talk at University of Warsaw. Thank you for the invitation. As far as the outline of the, oops, sorry, I'm sorry, I have to, oh, forgot it. Okay. As far as outline of my talk is concerned, I will start with introduction, motivations, then I will briefly introduce us to fluid equations for ions, electrons, and neutrals. Subsequently, I will discuss, or rather actually present our plasma surgery tool, which is the our code, Joanna code, some applications of the Joanna code, and finally I will complete with a few conclusions, two conclusions in fact. As far as the structure of the sun is concerned, so we know that the sun consists of a core, which occupies more or less a quarter of the solar radius. And well, then we have the radiation zone, convection zone, and finally we arrive to the solar atmosphere, which consists of three layers. The bottom layer of the atmosphere, it is called the photosphere. In the photosphere, we have such characteristic structures as sunspots, for instance. The solar photosphere occupies a region of about 500 kilometers, and 3 times thicker layer which caps the photosphere. It is called the chromosphere. In the chromosphere, we have, well, actually, there are some nice structures. I should perhaps also mention that, or maybe I will say that while looking at the next slide. So above the chromosphere, there is the solar corona, which actually has no clear outer boundary, as it smoothly transits itself into the solar wind. Here is the as some drawings for the solar atmosphere. So we have the convection zone, which is of course convectively unstable. So we have some very characteristic structures which are present over here, like the granulations, crowdy structures. So that means they join themselves in bigger structures which are called supergranulation. We see here supergranulation. An average size of a granule is about 1,000 kilometers, 1 megameter. Okay, supergranules occupy a region between magnetic network structures, like we see here, magnetic field lines fanning out into the chromosphere and high up into the corona, and creating such like a canopy, like canopies, like jets, like fibrils, like some other, actually, a diversity of structures which take place in both in a very dynamic region, which is called the convection zone. So convection zone is a source of the main source of energy, at least kinetic energy, on the sun, and somehow this kinetic energy is transported to the atmosphere through the chromosphere. I should perhaps say here that the photosphere, the average height of the photosphere is 0.5 megameters or 500 kilometers, and the chromosphere is 3 times higher. Well, it is divided into 3 sub-regions, but perhaps that's not that much important. The corona is, as we said a while ago, it caps, or it lays above the chromosphere. Well, as you see, this is of course a sketch, but you see a plethora of phenomena which take place in the solar atmosphere. Some of them won't be discussed today, but and some of them we will focus a bit, but it will be in a while. So I would like now to refer to the semi-empirical model of the solar atmosphere, which was devised by Avret and Loser in 2007. They have a newer paper, a bit newer paper, but the older one is slightly, which I like more. And what they did, they actually somehow inferred from their observational data, spectral data, temperature in the photosphere, which occupies this region, 500 kilometers. It is 500 kilometers thick region. And the photosphere at its bottom is well, roughly, say, 6,000 kelvins, and this temperature subsides with height, which is expected, but counter our intuition, this temperature starts rising up in the bottom chromosphere until it reaches a sort of plateau over here, and at the transition region, which divides the chromosphere from the high up laying the corona. At this transition region, temperature reaches, say, megakelvins values. Just say 3,000 or maybe 10,000 kilometers from the surface, from the surface of the sun. So from the bottom of the chromosphere. This is one of the central puzzles of the solar, actually, heliophysics, and we don't know why does it happen. It simply it is counterintuitive to our terrestrial conditions. Further out from a source of a heat, we expect the temperature supposed to subside, but apparently that's not the case. So I will comment on that a little bit. Actually, that's one of the topics which drives our interest into the solar atmosphere, but we should perhaps have a look at these plots, which show neutral hydrogen, concentration of a neutral hydrogen versus height. So, well, it subsides, that's okay, we should expect that. With height, we have also concentration of electrons, which somehow subsides, which has some wiggles over here, but anyway, I wouldn't discuss it in more details. But if we assume quasi-neutrality of plasma, so it means concentration of ions equals concentration of electrons, so we see that ions in the photosphere are up to, say, 10,000 times more neutrals than ions. In the chromosphere, particularly at its top, the number of ions equals more or less a number of neutrals, and in the corona is fulfilled by essentially fulfilled by ions. All right, so and another puzzle is associated with the origin of the solar wind. So here's the reference to the famous Parker paper 1965, in which he drawn velocity of the solar wind versus radius in units in megameters. Okay, so we see that for a given temperature, say 1 megakelvin temperature at 10,000 kilometers from the surface, the velocity is 200 kilometers per second, and high up it rises with the distance from the sun. That's unclear. That's this acceleration of the solar wind. That's a puzzle, which we can't solve it up to now. It is known well for more than 5 decades, and we still don't know how to solve it. Well, but actually, I would not study this because we are not ready. We do not focus on this acceleration of the solar wind. We rather focus on the solar wind origin. Somehow, the solar wind has to originate at the solar surface, but we don't know exactly from where. We don't know anything about a nascent solar wind. Oh, maybe not anything, but we don't know very much. So still there's some debate how the solar wind is generated and where it is generated and so on. So here are our main motivation. So simply we want to contribute to the research on atmospheric heating and plasma flows. A number of papers were published, both on atmospheric heating and plasma flows or outflows, essentially. But also we are driven by our curiosity. We simply want to study phenomena because they are there, because we know that the solar atmosphere is partially ionized, but we have neutrals over there and we have ions. All right. So now we have to devise a model, a mathematical model for charges, for ions and electrons, and for neutrals. Of course, well, the solar atmosphere does not consist only of ions well, sorry, I should say that actually it's more complex than I am displaying here. So we have only, our model is the simplest conceivable, but still it is better than a magnetohydrodynamic model, which actually treats, which deals with, or which describes ions. So we have neutrals, ions, here conservation of mass equations, and these neutrals and ions, they interact one with each other. Those two species interact one with each other through collision forces. So here we have some drag force associated with collisions between beta and alpha species. Alpha and beta are coefficients, subscripts which run through I, E, and N. In the energy equations, which are written over here, we have terms like capital Q. The capital Q contains a term heating associated with collisions. Well, so collisions are essentially work, I should perhaps say that collisions work essentially as internal friction. So kinetic energy is released in the form of heat, but we have also some extra term, which corresponds to the fact that a warmer species actually transfers its energy, a part of its energy, into colder species. Induction equation written in a little bit implicit form, but if you don't mind, I would not discuss it because it's rather technical. And but electrons, we have also in our model electrons. Well, ideally, we would like electrons being described by well, a sort of fluid equations, but having electrons in the model is very challenging because well, electrons are, of course, associated with electromagnetic forces. We don't want to have them. I mean, we would like to have them, but because of computing facilities, actually, which are required. There are no, I should say clearly that there are no such computing, nowadays there are no such computing facilities worldwide, which would allow us to describe electrons, okay, fully electrons. So what we do, we just want to have a little bit electrons with, in the sense, in this way, okay? So that's our assumption, very crude treatment of electrons, but at least they are there and they provide some, through the collisions, they interact with other plasma species, and we assume that plasma is quasi-neutral. So this assumption removes a number of waves in the system. So it's a crude simplification, but still it is okay, for at least for now. And the velocity is derived from the definition of electric current density J, capital J. So you see this equation. Well, okay. So that's not our. This is the assumption or treatment of electrons, which was used in the literature by Gabor Toff, for instance, or well, by some others. We have actually. I should perhaps say. Oh, I'm sorry. I should perhaps say that I wrote here down the equations which are in a sort of ideal form. Ideal, that means that we don't have explicitly written ionization, recombination terms, well, thermal conduction, there are no thermal conduction terms, there are no viscous terms, there are no resistive term, magnetic resistivity terms, and so on and so on. But those terms are they are implemented into our code. I would not discuss details because it would be rather too technical, but let me to say that actually about few of them. So we have non-isotropic thermal conduction. So thermal conduction is essentially along magnetic field lines. That's a standard, well-known assumption. And some other terms like Hall and Biermann battery terms. Biermann battery term is quite interesting term because it is responsible for generation of magnetic field. And on the sun, it is not very effective because this term can be can generate magnetic field in the from kinetic energy. Kinetic energy can be transferred into magnetic energy, but magnetic fields would be generated not that much strong, of the order of, say, a few Gausses. So it's really not what we much want, and they are not well tested. So we have not used all of those two terms yet. Okay, and we use the opal solar abundance model. So in which mean masses of ions, electrons, and neutrons are evaluated like that. And you see that we don't take that the mean mass of ions is higher than one I mean, in hydrogen mass. So it's really, we take into account some other plasma constituents. So that's according to this model, opal solar abundance model. And having temperature profile from the model of average and loser, we can construct analytical expressions for mass densities, for gas pressures. So if we assume that the solar atmosphere is hydrostatic, we can draw the ionization fraction, which is the ratio of neutral concentration to ion concentration. You see that at the bottom of photosphere, gravity points to this way, so that's a height. And the more than 3,000 neutrals, but subsequently in the corona, which occupies this region high up, this ionization fraction declines with height below to low values. So there are very few neutrals in the corona. Okay, and now applications of our code. So I will start with a very simple but still challenging problem, which refers to ion neutral acoustic waves. So for a while, I will assume that the solar atmosphere is magnetic free, and at the bottom of the photosphere, I set a piston, which is described by a sinusoidal wave. So here we have a piston operating up and down with this velocity. PD is just a period, and period is taken 5 seconds. So we need short periods, because for short periods, two fluid effects are more important. Still 5 seconds is too much. It's too large period because collision time is very low. It is collision frequency is of the order of, say, megahertz. So it's just 10 to minus 6 collision time. But anyway, we start with that, and we see, first of all, we see that this piston, although it has a very low amplitude, which is sonic and subsonic, much subsonic, sound velocities of the order of, say, 5-10 kilometers per second. So it's really very low, but so the nonlinear effects are not important over here, but due to gravity, which points to the left in this figure, the wave grows with height. So we see this growing envelope with height. And here actually are two plots overlaying one each other, ion velocity and neutral velocity. And A corresponds to the bottom of the photosphere. So those actually two curves which are zoomed over here. So they are still hardly distinguishable, but in the chromosphere, in the top chromosphere, we see the difference. So one, there is some drag between ions and neutrals, and that's good. Actually, that's good, because if we have this drag, so there's a chance for kinetic energy being transferred to thermal energy, and in fact it takes place over here, because if we draw here, the so-called time distance plots for relative perturbed temperature. So delta Ti is just temperature of ions minus initial temperature divided by initial temperature. So at T equals 0, we have a piston operating over here, and there are no waves, essentially. Well, you see that there are no waves in this region, but later on, we have acoustic wave propagating upwards, and being reflected, while reflected from the transition region, a standing wave pattern is being sustained, and this standing wave pattern results in some heat being released at some regions. You see some regions. This effect is even more pronounced for higher wave periods, and that's a puzzle, I must admit. So somehow we have to, we wait for those results to be checked, because PD equals 30 seconds. Driving periods 30 seconds, it's far more than the collision time in this region. Collision time in this region is something like 1 second. Well, and even nevertheless, so up to one second. But for a large wave periods like 300 seconds, we have compression and rarefaction. So we have both heating and cooling, but essentially the so-called 5 minutes oscillations, which are present in, which are generated by the solar granulation. They don't play any role, at least directly, in heating. Let me now to introduce to the problem, to the Riemann problem for Euler equation. So we have a tube, and on one side we have a diaphragm, and on this side, so that's an obstacle, and here we have a higher velocity. Yes, higher gas pressure. Here is a lower gas pressure. So that's at T equals naught, but at T higher than naught, if we remove this diaphragm, so we'll see a rarefaction wave being propagated to the left. That's a mass density, seen in mass density, and shock. So shock will propagate from the region of higher gas pressure to the region of lower gas pressure. And we have also something which looks like a shock, but actually it's a pseudo shock. So we have a discontinuity in mass density, but it's not a true shock. The true shock is over here. So that's a true shock because of the other plasma quantities like velocity, like gas pressure, they also experience discontinuities. But this shock, well, the pseudo shock it is called pseudo shock because it is seen in only in mass density. Sometimes it is called contact wave, entropy wave, but I like to call it pseudo shock because it's not a true shock. And one of our projects was actually associated with those pseudo shocks, and which were observed on the sun. So that's a chromospheric level, and this white region corresponds to a denser plasma, dark region corresponds to rarefied plasma. I will perhaps show that was too much, 4 still frames. So we have condensed region and rarefied, the opposite. Maybe I will show this. So we have dense region being followed by rarefied region. So we try to explain it in terms of pseudo shock, because if we run the simulations, so we see simulations, gravity points to downwards over here along the y-axis. Here is logarithm of mass density, of ion mass density. So at this point there was some gas, a pulse in a gas pressure was launched, and this gas pressure generated a shock. This shock is not seen, but actually a pseudo shock is seen. So pseudo shock, it is being displayed over here. Perhaps I will show 4 still frames. So pseudo shock is over here. This is just a place. So there is a diversity of pseudo shocks on the sun. And they are indeed this jet-like structure consists of a shock. Shock is not seen. Shock is high up, propagating along magnetic field lines, white lines, and so we have a pseudo shock over here and rarefaction tail or rarefaction wave. Okay, and now another problem, actually most challenging, corresponds to numerical simulations of a solar granulation in a quiet region. So we have a region at a time equals, initially at t equals naught, we have a uniform, unidirectional magnetic field, which consists essentially of a vertical component. Well, there's a transverse component. So that's a 2.5D model, not a 3D, I'm afraid, not yet. And we let it go. We let the code working. Perhaps I will show the movie over here. This movie plays over here. I started this movie at some late time when already granulation was generated by itself. So we didn't put any hand into this, but we just, we know that this region is convectively unstable. So we just seeded this granulation, convective instabilities by some random, very small random numbers in velocity. So it doesn't matter, in fact. Even numerical errors, which are present in every code, can sometimes seed convective instabilities. So here's a logarithm of mass density of ions. Magnetic field lines are displayed by dark black lines, and we see that a number of phenomena like O points or reconnections, blah, 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 and many things, in fact, so we can see it and analyze it, but also we have also downdrafts, which exhibit temperatures of say up to 10 kilometers per second. So they are really very fast, perhaps a little bit overlaid by magnetic field lines, but we see some dense plasma being propagated downwards. Okay, so that was our project. It is still our project, and whoops. Okay, so I'm sorry, I moved a little bit, but that's okay. So now if we actually, I will perhaps move it and explain what I meant. Sorry. Now what we do, I'm sorry, I cannot move this. Oh, now I can. All right. So what we did, we actually collect a signal along this line, so along a slit, numerical slit in time, and actually along and we average this signal over horizontal direction, and we ended up with a temperature profile which looks a bit similar to the average and loser temperature profile. So at least in this model, of course, it's not exact overlaying, but at least numerical data is quite close. Well, we can say, well, but it is relatively close to the observational data of average loser. So the collisions between ions and neutrals are able to sustain the chromosphere. Essentially, they can sustain the chromosphere. I forgot to say, which is very important, maybe not at this point, but well, it can be done in a while. And the second, so anyway, this curve is used as a sort of verification of our model. We want to verify our model. We want to have temperature profile which is quite close to the observational data, and the other verification comes out from the observational of Doppler velocity. Doppler velocity versus temperature, logarithm, doesn't matter anyway. So higher temperature means we are in the region of, in the corona. So we have here colder temperature, so that's a lower region by perhaps top of chromosphere. And we see the Doppler shift is higher, so we have a blue shift over here. So plasma flows downwards over here, all right, and here it flows outward. That's okay, because we want to have the solar wind. So the solar wind somehow originates, well, around this point, so somehow around this region. And that's the data of Keisha et al. And let me to summarize actually this data. Actually, it's not only his data, there's some other observational data. So different different symbols correspond to different set of data. Well, he has some authors. And so below the transition region, downflows of plasma observed. Above the transition region, in the low corona, we have upflows of the order of, say, 2 kilometers per second. Now the question is whether it is somehow observed in our numerical data. So I will show you similar. I will show you similar animations, but this time with magnetic field lines are displayed as before, but now I illustrate vertical velocity of ions, vertical components. So gravity points downward over here. Red colors correspond to outflowing plasma. So that's the plasma which leaves the sun, and there is also some downflowing plasma. And now our task is to average this over, say, horizontal direction and in time. And that's the figure which I will show in the next slide. Okay, so we see that up to, say, below transition region is over here. So below the transition region, we have downflowing plasma of the order of, say, with velocities of 5 kilometers per second. And well, at this height, we have outflowing plasma, so net upflows. So here somewhere there is the origin of, we can treat this height as the origin of nascent solar wind. So granulation is responsible, granulation is responsible for generation of a solar wind. Well, it's perhaps nothing special, but we try to really, we could expect it, in fact. Although I must say here that in order to get upflows in this region, the low corona, I have to heat it artificially. I cannot get upflows below artificial heating. So if I forget about heating, if I remove heating, this artificial term, so I have downflows, which is not observed. So I prefer to have this artificial heating term to get upflows which are observed. All right, and as a FET, so that's a second verification of our model. We want to have both upflows and downflows. We want to have observational data. I should perhaps overlay it by the observational data, which is here, but anyway, I have no time to do this. Okay, and as a FET verification of our model, we use a Fourier periodogram. So here's a vertical height at the bottom of the photosphere. The transition region is over here, and convection zone is over here. Granulation operates somewhere over in this region. So gravity points to the left, and we have some. Now, what we do, we simply at every height, we evaluate period of Fourier period. So what we see that actually in the convection zone is occupied by long wave period oscillation, something like, well, 300 in this region. Even higher wave periods are seen. Of course, it depends a little bit. I mean, those wave periods are exact values are vary a little bit depending on realization of a random medium, which is sustained by the granulation. But anyway, this, because 300 seconds, oscillations of 300 seconds are not able to propagate high up, they are evanescent. So we have to somehow transfer the energy to lower wave periods, which occupy the chromosphere and the corona. And somehow, well, he has two sets of observational data, only 3 points from K-Sharp et al., and also by Wiśniewska et al. They also provided us some data. There is some resemblance between the observational and numerical data, which made us happy. I just need 2 slides to complete, so I hope I'm not running out of time. So let me to summarize our findings in this way. So we have the sun. Oops, sorry, not this button. The solar wind is observed on the sun And we have also this chromospheric low coronal heating paradox. So these are warmer regions than the bottom of the chromosphere. So the temperature rises in these regions, surprisingly. And but upflows are observed, definitely, they are observed, and waves are observed for a long time, for decades. And we have granulation. We have the convection zone on the sun, which is a vast reservoir of kinetic energy. And so it's a matter only of finding a way of how to thermalize this thermal energy. And we have found that, of course, granulation generates upflows and generates waves. And upflows have a chance to generate the solar wind high up. Still, we have not made the corresponding simulations. We see some acceleration, but still it's not one-to-one agreement with the observation, with the model of Parker, say. And good that actually both upflows and waves, they dissipate. They dissipate the kinetic energy in the form of thermal energy. And so the whole system is being logically presented here. So we have granulation. Granulation is responsible for the solar wind and also for sustaining the chromosphere, not corona, low corona, perhaps low corona, but still higher up corona. Well, we need to find some other mechanisms how to heat the top corona or middle corona. All right, so magnetohydrodynamic model can work because we have we have some dissipative mechanisms like say viscosity, like magnetic resistivity, like say bipolar diffusion, which actually results from partial ionization. Or maybe I should actually emphasize here that two fluid effects are not important in the photosphere because the collisions are too frequent, but they are more important for in the chromosphere, more important for relatively long wave periods, the wave periods which have a chance to be observed. Okay, but two fluid effects, full two fluid effects of free fluid, or actually it would be nice to have helium in the model, but already we crunched numbers. Our model is too very often too complex. We recognize it as too complex, and we are tempted, or we are forced even very often to go one step backward and simplify it and try to figure out what is what. So I mean, we have to find a cause and a reason of a given phenomenon. Okay. All right. So finally two conclusions. We have collisional damping between ions, neutrons, and electrons, and some other plasma species which are not taken into account. Well, I would say that helium is maybe important, helium ions and neutrals, but that's perhaps for a long future, far future. But anyway, these collisions lead to chromospheric and low coronal heating. So the solar atmosphere can be sustained well with some extra artificial heating of the corona. So still we don't know how to heat the solar corona. And the granulation excites net upflows in the low corona, which may high up contribute to the nascent solar wind. Thank you very much for your attention. I really appreciate your presence.
Thank you very much. You can do thank you. We can have some questions from here, from the audience, if there are any. Please raise your hand first, and then I'll come with the mic. Questions, please. Okay.
Thank you, Professor Murawski, for this interesting talk. My name is Krzysztof Murawski, and I have this a question about other mechanisms that can heat up, that can contribute to the heating up of the corona, like micro or nano flares, which are, as far as I know, considered to be part of this mechanism.
Yes, exactly. Thank you for this question. I didn't mention that, but nano reconnections or reconnections actually they definitely can contribute to the heating. With reconnections in the chromosphere, it's a bit of a problem because actually cold material is ejected. So we have spicules, we have jets, cold jets, and those cold jets, they are very energetic. They are very energetic, but actually their energy is mostly associated with kinetic energy. They are dense. So dense and cold. So unfortunately, they are cold. So I don't know whether we'll find a good way of releasing so much energy from magnetic field to heat the corona. But definitely reconnections, which can potentially take place in the higher regions of the corona, they have a chance. They are good candidates. At least that's what is written in the literature, that they can, well, they are probably the main suspect of heating, suspect factors for heating of the solar corona. Yes, I'm not an expert on reconnections, but anyway, I hope, or I believe, that's my feeling, that reconnections may play the major role.
Okay, thank you. Any further questions from here? I don't see any. I just have a brief one. So this is all applied to the sun, but have you thought about should this mechanism work? Have you considered applying it? Have you tried for other stars which have strong solar winds, so strong stellar winds?
Not yet. What we, I mean, as far as the solar wind is concerned, generation of the solar wind, so usually people take alpha waves into account. They say, well, strong or large amplitude alpha waves, they are responsible for generation of the solar wind. Well, in our case, I mean, our model shows that, well, alpha waves, of course, are present in them. In the model, but they don't seem to play a major role. We have, I would say, slow magnetoacoustic waves, which are more important. Those waves are excited by the granulation, and those waves are sufficient to generate sufficiently strong solar wind. Sorry, maybe not solar wind, but outflows or upflows, and those upflows can high up generate nascent solar wind. No, I haven't. To answer directly your question, no, I haven't tried yet. Our group is very small. Okay, the problem with the model is, of course, there are many problems. I shouldn't really wrap up everything and say everything that our model is complete. And no, there are many problems, many issues. I didn't want to discuss it, but it's definitely the model which requires much attention. But as far as the solar wind is concerned, essentially, we would need to have it rewritten in the form of spherical coordinate, but it's still a challenging topic. Our group is small. Perhaps everyone complains about that. Okay, every group complains that it's too small. So it's nothing new from my side, but definitely, we have some. Well, I would say when we ran the code, when we wrote the code, we were very happy. But when we started using it, we actually see a few drawbacks. So I really prefer rather to focus on them. Still, I would okay. I would not say that we need some manpower, more manpower, but. Not yet. Anyway, that would be nice. I mean, sometimes I see jets, very strong jets, which eject a significant amount of plasma with high velocity, but actually I haven't analyzed some of the numerical events, numerically obtained events. So I really need more time. Well, maybe next life.
Okay, thank you very much. Let's thank our speaker again.
Thank you very much for your attention.
Thank you, and I'll stop everything. See you next week.